Good morning, everyone. I'm always testing the speaker to make sure that you all can hear me. I had one instance in the fall when I tested my speaker and everything was fine, and the kids kept saying this, I can't hear you, but they didn't have their video turned on, and then they didn't leave messages, or I guess they thought they could leave messages, but finally, a young lady came on and did this, and I said, "Oh, okay, you can't hear me," after like 5 minutes. So I'm always making sure that I'm coming across nice and clearly. Now, today, what we want to do is to continue with the volumes of the Solids of Revolution, and this will require a new technique. We talked about the cross-section method, the disc method, washer method, and this is just an alternative to those methods. And you may find that this is just interesting in its own right, not particularly that we need another method, but there are instances when the shell method will produce an integral that's simpler. For instance, you might produce an integral with the disk method and you can't find an elementary antiderivative and would have to approximate it with like maybe Simpson's rule. So sometimes the shell method can be very useful. And then there are certainly instances where you can pick one method over the other. For instance, you might look at a particular region and say, I think I could set up a simpler integral with maybe the disk method or maybe the shell method, or maybe you try one and the integral's really difficult. And then you say, well, let's see what the other method will give me. And maybe that'll be an easier way. So let me get to that. I thought about something that would be a little bit easier to give you a reason as to why this works. The disk method's real simple, but let me just go ahead and share my screen. So lots of times, the idea is that we get back to the partition. And so we analyze for one particular subinterval, and then we extend that to the entire partition, and then of course let the norm go to zero, and we end up with an integral. But here's what I wanted to do. I thought about this morning. Of course, this is written up in your lecture notes, but I thought I might just use a little simpler notation here. So we're going to use what we call cylindrical shells. Now, when I take the opportunity to talk a little bit about how the method works, that's only because I want you to have some understanding, and hopefully the method won't seem so abstract. So what I'm going to do is I'm just going to draw Professor Ron's cylindrical shell. And let's see here, I practiced this morning, so hopefully the picture will look okay. So we'll do an inner cylinder and then an outer. So just a little bit of artwork here. Maybe not the best. And now what I want to do is I'll go ahead and extend and use some real simple notation. And then of course, at the end, we can switch to whatever variable the problem gives us, X or Y's or whatever the case may be. And we'll continue over here. So, and now what we can do the height dimension. with a dotted line too. And do the same on this side. So now what we want to do is draw an axis, because we're going to think of revolving just like we think of revolving a strip to create a disc. So the idea is that creating this particular shell would be the result of rotating a strip about an axis. But in this case, the strip is parallel, so we get the cylindrical shell. So what we can do here is go ahead and mark this off as an R for the inner. So for the inner radius, we'll have R. And then, of course, we'll have the delta R here. And you can think of this as an X and a delta X. I'm just using R for radius. So we'll say inner, for the inner shell, we have a radius of R. And for the outer, we have R plus delta R. And then, of course, we have a height. We'll just call that H for now. So the idea is that you can look at this and say, well, this might be a little bit more complicated than the disc, but it's still the same type of geometry going on. So for instance, if we took the strip and we rotated it about an axis, say the vertical axis, then we get this shell. And then we might say, okay, well, before we got the volume of the disc, how do we get the volume of the shell? Well, again, we'll cheat a little bit. We'll say, well, you know, we actually know the volume of a cylinder. And so we'll use that from our high school geometry to get some kind of formulation. So we'll say volume of shell. And this is very intuitive. You know, everything is not always difficult. I think we find that we have to spend more time doing antiderivatives and arithmetic in this class than anything. Sometimes the derivations are kind of refreshing. So we'll say the outer cylinder volume will be pi r squared. And so we have the outer radius is r plus delta r quantity squared times h. And then, of course, this is just like doing the areas. We want to subtract the volume of the inner cylinder. So you're seeing a lot of the terms will absorb. So we'll have pi r squared h. So we didn't have to do this before, but at least this idea just utilizes the volume of the cylinder that you talked about in your high school geometry class. So let's go ahead and note in both cases we have a pi h, so we can go ahead and factor that. And then, of course, what do we do in this class? We expand binomials, and unfortunately, we're stuck with it. So we have r squared plus, of course, 2r delta r, remember the product times 2, plus delta r quantity squared. And then, of course, here we just have the minus r squared. So now we have pi h, and we'll just do a little bit of algebra to this to give us a form that will be useful for our integral formulation. Notice the r squares absorb, and we have 2 r delta r plus delta r squared. And you're thinking that looks kind of odd. How is that going to help us? But we can factor this also. So now let's just go ahead for convenience and convention, factor the 2 delta R from each of these terms. So we'll have a 2 pi h delta R. And then notice here, when we look at what we do here, we've got the 2 and the delta R extracted, and we have an R left behind. And then, of course, here with the factorization of the 2, we have to pay for that. So we have a delta R over 2. Now what we want to do is show that we get like an average radius, like between the R and the R plus delta R, so we can get a common denominator. So the hard work is done, not that this has been overly difficult. So now we have a 2R plus delta R divided by 2. And at this point, I just want to break up the 2R into 2 copies of R. Now what you see, and this is the same derivation that you'll see in your notes on Blackboard. What we have here is an average of the inner and the outer radius. So that's a very convenient way to think about writing an integral definition. So what we do is we just use a common notation here. We'll just say average radius. And I think the notation the book or text uses is just a P. Sometimes it's a rho, but I'll use P. When we do center of mass, we'll use rho, and that'll be a Greek letter. And then the H here, we just say height of strip, or length if you like. We H for the, formula letter. So now, when we write this, we can say 2 pi, and then we can have P, then the H, and then the delta R. So this is like maybe like the disk method. Before, with the disk method, we had the pi and the R squared and the delta X. And since we're using R's here, we're thinking we can just switch out the R's with X's or Y's depending on the algebra of the particular problem. So now we can think of this as possibly 2 pi with an independent variable X, P of X, H of X, delta X, thinking of this delta R as a delta X, or maybe we're using an independent variable of Y. So we have 2 pi, P of Y, H of Y, delta Y. So the idea here is that even though this is a little bit more complicated than the disk method, because again, we're generating a shell, just utilizing geometry that you already know, we already see a very straightforward relationship here. So now, if we were thinking about the volume of a solid of revolution using the shell method, this would imply that we just do this argument for each interval of the partition and then sum and let the norm go to 0. So this would mean volume of solid of revolution. We'll just write it, we'll write it in the X variable. Volume of solid of revolution using the cylindrical shell. And notice here, and this is always a thorn in your side, we don't just have the pi. Because of the manipulation here, we have the 2 pi. So that's the difference between the disk and the shell method. So we have 2 pi, and say we just have an interval of integration a to b. Then we'll have our p of x, h of x, dx. So maybe if you think about what we did here in the sense of just deriving the formula, this makes more sense. But if you just look at it and you don't think, well, where did this come from? That doesn't make any sense. The disk is, you see that power squared and that boom, that just comes right to you. But now what we're having to do is think of this average radius. And one thing that makes it a little bit easier is that you can think of this as the distance to the axis of revolution. Like if you think of this as a strip here, we can think of the P, or the average radius, as just basically being the distance to the axis of revolution. So I'm going to write that in: distance to axis of revolution. So again, what's nice about the calculus is that as it has evolved, nice terminology comes into play. We think about the inner radius and the outer radius for the washer method, or just the radius for the disk method. And then of course we have a cross section for the cross-sectional area method. Here we're thinking, when we draw the strip, we figure out the distance to the axis of revolution. And then in terms of whatever algebra we have, we find the height of the strip. And then take the product, in that case, integrate from whatever interval we have based upon the problem, and then the multiple 2 pi. So when you practice this a couple of times, it will become a little bit more commonplace. So what I thought I would do to start out is to do this again. Sometimes a simple derivation can make the whole concept simple without having to kill it with a lot of partitions and things. That concept is intuitive to you. And I wanted to keep this in a geometric standpoint so that it would make sense. Let me get rid of my email so it won't ding on us the whole time. Okay, so now let's take our newfound friend, the cylindrical shell method. Now for short, of course, we're lazy. We just say shell method. Shell method. You can certainly say cylindrical shell method, but I think I'll probably stick with shell method. That's like saying the circular disc method or whatever, but we'll go with the shorthand. So let's look at an example. Now, again, with lots of these problems, the exercise will say use the shell method. Now, there may be instances where the problem will say you choose. So, but at least initially, let's get some practice with the shell method and actually work with it. So here's an example. So we have a region. So let's just say in this case, our region will always be bounded by curves. In the more general setting, we say curve instead of function, but some kind of equations that give us curves when we graph them. And so we'll have y equals the square root of 2x minus 5. Good old college algebra transformation. And then we have y equals 0. And then we have x equals 4. And what we want to do is revolve region about the x-axis. Well, no, in this case, let's go ahead and do the y-axis, about the y-axis, and then compute the volume of the solid of revolution. Lots of words. You can think, well, just compute the volume if you know the context. So what we want to do, again, just like we were doing an area problem like we did with the disk method, we want to see what we have, and then we can write in the distance to the axis of revolution and make sure we have all of our variables correct, at least for the independent variable that we want to use. Now, first, what we can see is, let's look at this radical here. Let's go ahead and factor it a little bit. Let's factor the 2. So when we factor the 2, we get the x minus 5/2. So what we can see is, in this particular case, when we think about this, the square root of 2 will factor. So we're thinking of the radical being stretched because the square root of 2 is bigger than 1, multiplying the function by something larger than 1. And then, of course, we have a shift to the right by 5/2. So this kind of gives us an idea of what our picture is going to look like. And so let's go ahead and draw that. And then we can fill in the other ideas. So we have our y-axis. The region picture is always very useful. It kind of organizes everything as we've always done. And so now we can mark some of this off. So 1, 2, we'll spread it out a little bit so we can see it. Go ahead and mark in x equal 4. The vertical line. And now 5/2, that'll be 2.5. So we'll mark right here. So this will be our 5/2. And note here, let me just write this out. We'll just say x equals 4. So we have y equals, so we'll have what? 2 times 4, that'll be an 8 minus a 5, 1/2. So that gives us square root of 3. So we can mark this off. So when we cross here, we've got about square root 3. So let's go ahead and draw our square root function. Good old college algebra. Of course, this just keeps going. There. So again, we see it stretched vertically, but it's also shifted horizontally. So now we think, okay, well, here's x equals 4, and here's y equals 0. And we want to do this kind of manipulation. That is, we want to rotate this particular region about the y-axis. Now, let me just go ahead and just do a little bit of shading here so we see exactly what the region is. And notice how this one is set up very nicely already with the independent variable that we need. So again, let me just kind of motion here that there's the 5/2 there. I wrote it over to the side a little bit. I want you to know that that's the point there. So we're going to let x live, in this case, between 5/2 and 4. And so we can take an x. It's always nice to have room to draw the x, and then draw in our strip or our rectangle. So here's our strip. again, remember the strip is parallel to the axis of revolution, not a washer method. Now, when we look at this and we think, okay, well, when we're thinking about the average radius, remember that was the P. So I just said, let's just write that as the distance to the axis of revolution. So if we're given an X here, the distance is just this right here along the X axis, which is indeed X. So we say P, or the distance to the axis of revolution, is just X. So sometimes it's really very simple and we don't have to make any adjustments. But again, we're thinking, what is this distance? We just say X minus 0 since we have the Y axis. Now, of course, the height of the strip will just be from the X axis, Y equals 0, to the curve. And so that's given by the curve. So we can say in this case, H, or the height of the strip, will just be here. We'll just go back to this formulation and we'll use the 1/2 power, 2x minus 5 to the 1/2. So the idea here is to take a little bit of time to make sure you set these up, and because there's so many pitfalls with these problems. I mean, this is where Calculus 2 students think, well, this is like doing an optimization problem in Cal 1. You know, you set up the problem, you set up the function, you get the domain, and then you do the differentiation. And if you did that right, you get your critical numbers, you test them. I mean, it goes on forever. So we're seeing that the problem length is getting, is increasing. So now with everything that we have here, again, we have the distance to the axis of revolution and the height of the strip. We can go ahead and write down our integral. So we have volume. Remember the 2 pi as opposed to just pi with the shell method. So again, I'll just write here shell method. Shell method. And so now, lower limit 5/2, upper limit 4. And now when we look at everything, we have our X and we have our H. And what's nice about this, you're thinking, well, this is another miscellaneous substitution. But again, miscellaneous substitution can be done many different ways. So don't worry that you get different techniques for this. They all give the same thing when you get to the finish line. I try to do the squaring because I think it's simpler. So of course my WebAssign, it always wants to time out and then it makes the screen dark. So I don't know. Everybody comes up with these new ways to keep our website safe. So now what we want to do is just do a simple substitution. So I'll just say miscellaneous substitution. So now what we can do is just set the radical equal to our u. So u equals the radical. And then of course, this is a complete change of variable, not just a simple substitution. So we change out everything. So now u squared will be 2x minus 5. So now we can do the differential with that if and only if, let's just go ahead and do a little bit more work. 2x equals u squared plus 5. And so now x will just be 1/2 that quantity, u squared plus 5. So let's just go ahead and put boxes around things that we're going to use to change out the integral. Of course, we have our initial substitution. So this will replace the radical this will replace the x, and now we need a dx replacement, so we'll do the differential. So we have 2u du equals 2dx. Again, 2dx. And of course, the 2's absorb, so we have u du equals dx. So now when we look at this particular problem, the only thing left is to say, okay, well, what happens to the limit since we're changing out everything? So let's go ahead and do that. We'll say u of 4. So here we're going to put in 4. We've seen this before. We already know what it is. That's just going to be square root of 3. I'll write it again. 2 times 4 minus 5 to the 1/2. And of course, that will be the 8 minus 5. So that gives us the square root of 3. And then u of 5/2, that'll be even better. Again, we factor here, so u of 5/2 will just give us 0. But I'll write it out. 2 5/2 minus 5/2 1/2. So we just basically get the square root of 0, which is 0. So at least with the miscellaneous substitution here, we get a lower limit of 0, which we know is a big plus doing integrals. When you've got a lower limit that's a fraction, it does take a lot more work as far as arithmetic, as we all know very well. So now we can transform the original integral into the new variable. So moving our equals from here down to here, we get the 2 pi. Don't forget the 2 pi. The 2 pi can, lose its way. And then, of course, the lower limit is 0. The upper limit is the square root of 3. And now we can change everything out. So we get 1/2 u squared plus 5. There's our x right here, 1/2 u squared plus 5. And then, of course, the radical is just u times u. And then dx is just u du. Okay, now at this point, we just want to clean everything up. We can go ahead and bring the 1/2 out. So this will be a 2 pi divided by 2, 0, square root 3. And of course, now we have a u squared plus 5 times the u squared du. So now this is just going to turn into a power rule problem, which was the whole reason we needed to do this. So of course, the 2's absorb. Again, just remind yourself of the optimization problems from Cal 1, and then you find yourself at home. So now we've got what, u to the 4th plus 5u squared. Now the idea here is when you look at this problem, you're thinking, okay, well, this is really straightforward and simple. But again, you have to kind of go back and say, how did the problem evolve? And there is a lot of work to be done. It's like once you get to the finish line, you breathe a sigh of relief. But now you can rest assured that what you've done has given you a very straightforward integral. So now, let me shift this up a little bit. So we'll go ahead and add 1, divide by the new power. So we get u to the 5th over 5 plus 5, and then we have u cubed over 3. So I'll put the 3 under the 5 and the u cubed. And then we'll have 0 root 3. Now, again, we notice that the 0 annihilates these terms, so we don't, that'll be easy. So we have pi. So now we're going to substitute the root 3. So this will be 3, in this case, to the 5/2 divided by 5 minus 5/3 3 to the 3/2. And then, of course, the lower limit zeroes out both of these, so we can just say minus 0. Now, just to remind you, 5/2 equals 2 1/2. 3/2 equals 1 1/2. So that makes it easy to figure out the powers. So now we get, in this case, we get a pi. And so with the 2, we'll get a 9 times the square root of 3 over 5 minus 5/3. Well, notice here, we can make life a whole lot easier on us. Just go ahead and ride the wave. The 3 will absorb one of the 3's here and just leave us with a square root of 3. So we have minus 5 square root 3. So let me grab another sheet of paper, finish the calculation. So at this point, we're thinking, all right, we can factor the root 3 and get a common denominator. So we'll have pi times root 3, and this will give us a 9 over 5 minus 5. Now, one thing that we want to be sure here, and this is something I've noticed, the plus here, that's a plus. I don't know why I changed that to a minus. I want to make my numbers too small. And so when we look at this and we think about what we're doing, we just want a common denominator. Again, as we move through here, always go back and scan everything. It's always easy to write a plus where you want a minus and vice versa. So now we have pi times the square root of 3. So we can get a common denominator of 5. So we have a 9 plus, and of course, a 5 times a 5 is a 25. So now this gives us a pi times the square root of 3. And then, of course, the 25 plus the 9 gives us a 34, then divide by 5. And then we can make this look a little bit neater. So we have 34 root 3 pi divided by 5. So we really get some odd looking answers here. I mean, we think about where we start, drawing the region, setting up for the shell method, and then working the integral that we get, miscellaneous substitution, complete transformation of the integral. Miscellaneous is complete transformation, changing limits, everything. The integral, the new integral, fundamental theorem of calculus, and we get 34 times square root of 3 pi divided by 5. That's about as irrational as you can get, and transcendental to boot. So when you think about a volume of a solid of revolution, the idea is we had a little breather with the cross sections. It just really depended on how complicated the actual area of the cross section happened to be. In those cases, we got some nicer numbers, but with the disk method and the shell method, washer method, we're stuck with these interesting transcendental numbers. And of course, the culprit is pi. Transcendental numbers are even more odd in the sense and more distinguished, because they're not zeros of integer polynomials like irrational numbers like the square root of 2 or the square root of 3. So they're even more distinguished, and there are just as many of them, even though we don't spend a whole lot of time with them outside of what pi and what else? The base E, right? Okay, so let's look at another example. Now, when it comes to the shell method, there are all kinds of interesting problems. And what I want to do is give you an example where maybe we have to change up the variables a little bit. I always like to give you examples where we have to do a little bit of algebra to switch to another variable, just so we can get practice with the different methods. So here's an example. We have the following region, simple region, but it'll give us an opportunity to do some good algebra. So we have y equals 1 minus the square root of x. So again, good old transformations from college algebra. And then we have the line y equals x plus 1. And then, of course, the x-axis, well, of course, you don't know, of course, we have the x-axis. And here's what the problem says, revolve region about the x-axis. Revolve region about the x-axis. And then compute the volume of the solid of revolution. Compute the volume of the solid of revolution. So now when we think about this and we think about what we have here, this is a nice college algebra problem. So let's do some college algebra. So the thing is that you set these equal and you start squaring things and you get extraneous zeros. But let's just say we just have a walk down memory lane. This is good, and it's good to review this. So for instance, when we look at this, we start with the square root of x, just walk down memory lane. And then we do what we call an x-axis reflection. This is what I teach my pre-cal kids. This is so much fun, and it's universal. So when you're in physics and engineering, certainly use these. So we slap an x on the function, and that gives us the x-axis reflection. And then we do an upward v-shift by 1. So upward v-shift by 1. So that'll give us, if you like, we'll just write this first and then add the 1. So when you think about this, let's just think about moving some real simple points because we're lazy. Say we have 0, 0. Then, of course, we have 1, 1, and then 4, 2. When I teach this, I always give my students, kind of like when you do trigonometry, you think about principal points that are easy to write down and then easy to move. So now what we can do is do the x-axis reflection. So that means that all of the y terms, coordinates, will get negatives. So we have 0, 0, 1, -1, and then 4, -2. Now we do the upward v-shift by 1. So now we add 1 to all the y coordinates. All the action is happening in the y coordinates. So we get 0, 1, 1, -1 plus 1 is 0, and then we get 4, -1. So this is what you do in your college algebra class or review in your pre-cal. Let me give it a little bit more room here. I don't want to get too close to the edge. Let's just give a little bit room so when we graph our line, it's not so difficult. And spread this out a little bit more. So now we have a 0, 1. And then we have a 1, 0. And then we have a 4, -1. So 1, 2, 3, 4. So I'll have more here than we need, but still just good practice. So when we draw our function, just connect it. So there's our new function, at least the abbreviated part of it. And now we're thinking, okay, what about this line y equals x plus 1? We've got y equals 0. And this is y equals 1 minus square root x. And then, of course, for y equal, again, we clearly have an intersection point. So we'll say y equals x plus 1. So we have 0, 1. And while we're at it, let's just put in, a -1 if you like, just to see where we intersect the x-axis. So we have -1, 0. So I'll go ahead and move this over right here. So we see that the curves intersect at one point, but that's it. So now we can draw the linear function. So we have y equals x plus 1. And we want, again, now we can see that the three curves give us this region here. Nice curved region here, again at square root, nice and curvy. And then the linear part here, and then of course the linear part here. And what we want to do is revolve about the x-axis. So now what we can see is that when we take the strip parallel to the axis of revolution, this will just say, okay, we have a 0 and a 1. So we're going to take y to live between 0 and 1. And so we can mark off a y here and draw in our strip. So here's the y right there. And so now we're like we had with the last problem. The distance to the axis of revolution is just y in this case. So sometimes the p part is the easiest. So let me just go ahead and mark this in. Little curly brace there. P will just be y. That is the distance to the axis of revolution. And then we need the strip height, h. What's that going to be? Well, when we look at this, we have to do the right minus the left. So we need everything written in terms of independent variable y. So first, let's just go ahead and do the algebra. We have y equals 1 minus the square root of x. So this gives us square root of x equals 1 minus y. So we need a quadratic. So we'll square everything out. So that'll be x equals 1 minus y quantity squared. If and only if x equals 1 minus 2y, again, 1 times the negative y times 2 plus y squared. So this gives us the right curve. Here's the right curve. And then for the left curve, we have y equals x plus 1. So now solving for x in this case will just be y minus 1. Just transposing the 1 to get x equals y minus 1. So we say left curve. Let me write this in. Left curve, right curve. So now we can solve for h. I can fill this in. Let's do the computation. So h equals, so we have right curve, 1 minus 2y plus y squared minus y minus 1. So we get 1 minus 2y plus y squared minus y minus minus plus a 1. So now we'll get y squared. Okay, negative y plus a negative 2y is a minus 3y, and then a 1 plus a 1 plus a 2. Now, when you look at this, I can go over here and just fill this in. Y squared minus 3y plus a 2. So like I said before, this just gives us practice utilizing a variable that we need for the problem. So we get to do the algebra. Now, another thing too, I don't want you to have to guess with your graphs and things. So use your college algebra. I mean, these are set up for that, especially quadratic functions are the same way. So now when you look at this, we've got all the limits are set up. We've got y living between 0 and 1. We have the distance to the axis of revolution. We have the height of the strip. So by definition, this implies now that the volume, I'll go ahead and write it out, will be 2 pi. And so the limit 0 to 1, distance to the axis of revolution, y, and the height of the strip, which we calculated here, y squared minus 3y plus 2 dy. So at least with the last one, we had all those radicals, so we had more arithmetic to do. This doesn't seem to be as busy, and we're grateful for that. But of course, we had more busy work. You can think of this like the miscellaneous substitution. We had a little bit more busy work to change to the independent variable y. So now we have 2 pi, 0 to 1. So let's go ahead and multiply this out by the distributive law. So we have y cubed minus 3y squared plus 2y. So now, one nice thing about Calculus 2 is that we find ourselves just going right back to Cal 1 and college algebra. And so there's some comfort in knowing that we don't have to really invent a lot of new mathematics. We're simply recasting what we already know, which kind of makes this a topics course. So now we can do the add 1 divide by the new power. So we have 2 pi, same old song and dance, right? Y to the 4th over 4. And then, of course, here we have a minus 3. And, of course, we've got y cubed over 3. So those are going to absorb. And then plus, well, here we go again, 2 y squared. Evaluate 0 to 1. Well, ones and zeros. How lucky, right? So we have 2 pi. I'll go ahead and reduce all of this. This will just be y to the 4th over 4 minus y cubed plus y squared. So go ahead and reduce that. And now we can use the fundamental theorem. So this gives us a 2 pi. And notice the lower limit will annihilate each of these terms. So we'll just get a 0. So we get ones, again, easy powers of ones, just 1. So we get 1/4. Well, how nice. Minus 1 plus 1. And then, of course, this just gives us a bunch of zeros. So we're lucky for this simple arithmetic. The ones absorb, and we get 2 pi times 1/4. And of course, the 2 absorbs into the 4, and that just gives us pi over 2. So the idea here, and this is a good example, since you have 2 different curves above, if you try the disk method here, you would need 2 integrals. Because if you did your strip perpendicular to the axis of revolution, you have a different upper curve here as you have here. And so even though the shell method requires converting to another independent variable, it does cut down. I mean, lots of integrals for these types of problems can tend to be problematic in the sense that you're negotiating different upper curves, right curves, left curves. You got different limits of integration, and they're just that tends to be problematic. So what we can see here with the shell method is that this was actually an improvement. But like I say, you are in charge. I mean, if a problem says ask you something specific about a shell method, you probably need to use it. Otherwise, you can utilize any technique you like. You know, you as I tell my students a lot of times, you are the one in charge. Now, what I want to do is an example having to do with the shell method that will help us generate the volume of a torus. Now this can be done many ways, and what the author does in this particular case is give us a little breather. That is, they don't, Dr. Larson doesn't introduce this in the disc and washer method because the shell method is a much better way to do it. And of course, when you get to Cal 3, you'll parameterize the torus. I'll say a little bit more. Basically, the torus is the inner tube. It's what we call the donut, so to speak. So I want to show you how the disc method can produce some really nice algebra and calculus that make the problem very, very doable. So here we go. We want to compute the volume of a torus. This is just the more, I guess, mathematical name for the inner tube or the donut. If you've ever inner tubed on a river, or we've all eaten donuts, we know the shape of those. So what it says is, in this case, before I give you this, I'm thinking, well, how are we going to generate this? We're going to use a circle. So I'm going to say region bounded by the unit circle, x squared plus y squared equals 1. And what we want to do is revolve region about the line, in this case, x equals 2. And we want to use the shell method. So the torus, sometimes, like I say, the donut or the inner tube. So when you think of generating one, you can do a little drawing here to mimic it. So there's one side, and then you can get the inner side by doing something like that. So that's the inner tube. It's like, you know, when you're learning how to swim, your parents put you in an inner tube to hold you up so you don't go underwater. So that the inner tubes are something we all know of when we're learning how to swim. So that's what we could call a torus. And later on, you can think that like I said before, we'll parameterize the torus in terms of parametric equations that make the calculus on the torus a lot more straightforward. But to start the story, we want to begin with computing a volume. So what we can do is, let's just go ahead and set this up with this as our axis of revolution. And so we'll set up the circle again at the origin, the famous unit circle, right? So let's go ahead and draw that. Calculus 3 is just taking everything you learn in these classes and reapplying it. So it's a fun class. So let's go ahead and give ourselves a little space. So we'll have a 1 here and a 2 here. So we'll go ahead and draw x equals 2. So there's the vertical line, and this will be the axis of revolution. So you can see how if we rotate a circle, we get the inner tube like we have here. So let's go ahead and mark this off. So we have plenty of space. And I want to do this in a way, we always want to do this in a way so we feel comfortable. You know, you want to make sure that if you use symmetry or you don't use symmetry, that you've covered everything. And there are many ways to solve these types of problems. There's no one set way. Then, of course, as you get to differential geometry past calculus 3, you'll learn new structures. Some of you will take differential geometry or differential topology at the university. Very fascinating material. Dr. Gardner at the University of North Carolina was one of the premier mathematicians who set up differential geometry with the technology. He is deceased, but the man was brilliant, and I was fortunate to be able to take a differential equations class with him. But one thing I got from him, other than noting his brilliance, is that he always said, now we have to follow the recipe when we do a differential equation. So I look at this and say, we're going to use the shell method. So we have to follow what? We have to follow the recipe. So let me move this over a little bit. Professor Ron gets in the way. And so the thing that I noticed about Dr. Gardner is that he always respected the mathematics, and he said, let's follow what the mathematics tells us. Lots of times students say, well, I don't know what it's telling me. Well, but we can at least look at what's given and work with that. So now you're thinking, okay, when we revolve this about this axis, we get this torus here. So what's a way that we can do this to keep it simple and then use a lot of nice geometry that we learned in Calculus 1 to make our calculations simpler? So what I'm going to do is first, we're going to we're not even going to use symmetry this time, if you can believe it. Let x, again, we've got a 1 and a -1 here, because I want to use some of the nice odd function symmetric interval from calculus 1. So we'll just go ahead and knock it out. So we'll have -1 to 1. And so if you like, you can just pick an x here, and we can draw a strip parallel to the axis of revolution. So there's our strip. Now, of course, we have the algebra of the unit circle. So this upper curve here is just y. If we just take a principal square root, will be 1 minus x squared square root. So now we're set up. I mean, we don't have to do all the complicated algebra that we did in the last problem, because we've already got a nice independent variable. So first, we're thinking we just need 2 copies of this to get the h. So h will just be this copy of the square root plus this copy of the square root. So we can just take, by symmetry, we can just take twice this. So this will just be 2 square root 1 minus x squared. I'll just go ahead and cover the entire circle instead of half of it, just to make it a little bit easier. Less distraction sometimes is good. So we can take this strip and just move it all the way across the circle, because x will run from -1 to 1. Now, of course, we need the distance to the axis of revolution, the p, that we found from our initial derivation. Now, this is where we have to look. What's the distance along the x-axis? Well, this is x, so the distance will be 2 minus x. So p equals 2 minus x. So don't guess at any of this. I think you all are very talented, and you've had good preparation to get to this class. And just like I say, use the diagram to kind of guide you as you go through it. Now what we can see is you're thinking, okay, well, we're going to get some integrals with radicals in them. Do we really know? Well, we know geometry and we know areas of circles. So I think we're going to find that we're going to get a really simple calculation. So now I'll just say here, shell method. Obviously, it's the shell method because of the way we've oriented the strip, shell method. This is a nice example you can teach your friends who you might be tutoring in calculus. So now we have volume. In this case will equal now, remember our friend 2 pi, and I'm not using any additional symmetry here because I've covered the entire circle, so we don't have to worry about that. But then we have the integral from -1 to 1. And then we have the distance to the axis of revolution. And then now we have the height of the strip. So we have times 2 square root 1 minus x squared. So I think the initial derivation we did kind of helped us out with the notation here and gave us maybe a little bit more confidence with this technique. Again, remember, all of these techniques are definitions. We simply do some algebra to motivate them. So these are not theorems in the sense of the Pythagorean theorem or the fundamental theorem of calculus. What we try to do with these types of problems is to motivate a definition that's universal. Now, notice we can just go ahead and multiply this out and see what it gives us. So we have 2 pi -1 to 1. So let's see what this gives us. So now we've got the 2 and the 2 here. So that's going to be a 4. So we've got 4 square root 1. Well, and I could have factored this and let me, before I do that, let me go ahead and do that. Let me just make it a little bit simpler. That just seems to be too much work. Before I do this, let's just go ahead and do this. I don't like to have numbers just hanging out in the calculation. So let's go ahead and factor the 2 here. So 2 times. Okay, just go ahead and get rid of that. That's in the way, and I don't need to carry it along. That's a waste of time. So this gives us 2 minus x square root. Just make the calculation look a little neater. I know you probably don't care, but I do. So now we have the 4 pi. Now we can distribute inside the integrand. So this will give us a 2 times the square root. So we have 2 square root 1 minus x squared. And then we have negative x times the radical. And this is where we get to use some of the theorems from your Calculus 1 class. So that's a little bit cleaner. Okay, now we can break this up into 2 pieces. So notice we have the 2 here. So we'll have the 2 times the 4, 2 times 4 pi, -1 to 1, square root 1 minus x squared. That's where we're going to use some geometry. And then for the last one, we have 4 pi, and of course we have the negative here, so we'll factor the negative. So this will be minus 4 pi integral -1 to 1 x square root 1 minus x squared dx. So of course this looks real complicated, but it's not. Based on what we already know, we can do this without having to result to some type of trigonometric substitution. First, I want to note here, and we'll do the easy part first. This is what we call a symmetric interval of integration. And notice this function is odd. Again, it is defined on -1 to 1, and if we replace x with its negative, we get the negative of this function. So this is odd function, odd function. and we have a symmetric interval. Symmetric interval. That's the theorem you do in Cal 1. Odd function on a symmetric interval. I'll write it up here. So f is odd on, we'll just say, negative a to a, symmetric interval. Then the integral negative a, you could prove this, you probably did, I'm sure you did this in Cal 1, is just 0. When you integrate an odd function on a symmetric interval, it already has origin symmetry, and it zeroes out. And so when I look at the theorem here, we have the same thing. We have an odd function integrated on a symmetric interval, 0. So that one's done using a theorem without having to do the calculus 1 substitution. Now, of course, you can miss that and do it and still get 0, but why? I mean, this is a really useful theorem, and when you do your Fourier analysis with PDEs, you'll use this, and we'll even have an opportunity to use this again in our class. And now, so we've gotten that, we know what that answer is going to be. And now we have 8 pi. Now this, we're going to have to write down what that is. That's just the area of part of a circle. Note that this is just this curve here to here. So the area below the curve above the x-axis, this is just half, this integral is just half the area of the unit circle. So let's do this. So we'll say 1/2 the area of the unit circle. So this is using your geometry, again, from here to here, just the upper half of the unit circle. And so now, and of course here we have minus 4 pi times 0. And that's using the theorem. And now we have 8 pi. Now half the area of the unit circle is just what? 1/2 pi r squared. So we have 1/2 pi, and of course the radius is 1. And then of course 0 times 4 pi is 0. So this gives us 8 pi times pi over 2. And the 2 absorbs into the 8 to give us a 4, and then pi times pi gives us pi squared. So when you look at this calculation, you're thinking, man, these are hard integrals, but they're not hard integrals because you actually know these. Remember back in Cal 1, when your professor said, okay, use the geometry, use the idea that the Riemann integral with a non-negative function is the area below the curve above the x-axis. And so when you think of this, that gives you half of the area of the unit circle, which is exactly what this integral is here. And then of course we have to multiply it by 8 pi. Now this integral looks a little bit difficult. I mean, not really difficult because you can use your substitution from Cal 1 and fine, you'd still get 0. But odd functions integrated on a symmetric interval are 0. The evens, remember, you can cut the interval in half, and hit it with a 2 because they're symmetric with respect to the y-axis. But odd functions are really nice because they have that origin symmetry. The areas just annihilate themselves on either side of the origin. So again, utilizing what you already know from Calculus 1 is very nice. And so when you do your WebAssign, it might be that the axis here is different. Maybe you've got a different distance here. You'll still have a circle. And so you'll use the same technique, and you can use these ideas that we've used in our lecture. You don't have to start from scratch and then think, oh, how do I do this? Now, I will say this. There are instances when you'll be working a problem like an integral and you get 0, and then you scratch your head and say, well, was that an odd function or did that have any kind of special property? Sometimes if you look hard enough at it, you can see that, but you might be working a problem and not have enough time to be able to analyze everything, and you get your zero, and then you keep your fingers crossed that you did everything right. But if when you're working through a problem, you certainly get a function that's odd and you've got a symmetric interval, then think about it. Make sure you set everything up right, because this is going to give you a quick answer. So again, put this in your notes and put it on a note card. It is a very, very useful result, and you should probably sketch out how you would prove it. Again, that would be a proof I would do in Calculus 1. Again, a fun proof and not hard to do. Okay, now let's look at some other geometry. I think it's interesting that when we have this shell method, we'll just take advantage of it. Now, when we think about a surface or a solid of revolution, the idea is, okay, can we get, we could get the volume of a sphere using the disk method. We just got the volume of a particular torus using the shell method. A torus is a solid of revolution. Now, there's another example having to do with the ellipse. Remember back in pre-cal, you talk about ellipses and you're thinking, okay, well, you can take an arc of an ellipse and rotate it. And then you get what you call an ellipsoid. Sometimes people say, well, that's the football shape or the shape of a football. So again, we can use the same technique here. And this is why I like the shell method, because it actually presents a nice cohesive method that's easy to use. So here's another example. So we have region bounded by the ellipse. But we're only going to worry about rotating half of it, because we don't, we're just going to take half of the ellipse, the region, and move it. We don't have to do the whole. But for right now, we have region bounded by the ellipse. This is the way the problem is stated, where the X and Y intercepts, of course, are positive. A and B are positive. The convention you use for the standard ellipse. The derivation is long, but the equation you get is easy. So x squared over a squared, y squared over b squared equals 1. So we want to revolve the upper section, in this case, about the x-axis. And we want to compute, this is a WebAssign problem where you do x-axis and y-axis. Compute the volume of the solid of revolution. So let's get a nice picture here. Again, we want to take advantage of our pre-cal. And when you get to Cal 3, you're going to use your conic sections even more. So let's just go ahead and mark the y-intercept, the B, and we'll mark off a negative A and an A, just to spread it out a little bit so it looks like an ellipse. I mean, a circle is an ellipse, it's just a special case. Okay, so go ahead and draw in this arc. Now, this is what I was saying before. What we want to do is revolve this way. And so all we need is the upper section. If we're going to create an ellipsoid, we'll just revolve this section. It's just like the same of doing the volume of the sphere. Okay, we're just basically the upper section of the circle. So when we revolve this about the x-axis, we definitely get an ellipsoid. That is a solid of revolution. So now what we want to do, at least at this point, we see that the y will run from 0 to b. So y runs from 0 to b. And so if we take a y here and draw our strip parallel to the axis of revolution, let's just go ahead and mark one off. Again, you can do this in your head, but the sketch is really nice. It gives you all the rudiments that you need, all the particulars. So here's our strip. Now I like the shell method because usually the P is very easy. So we're going to go ahead and write that down. The P is just the distance to the axis of revolution, which is y. So that's easy. So now what we want is we want the distance or the length of the strip or the height of the strip, the h. And so basically it's like the circle. We just want to solve for x in terms of y. So we'll just say here, we'll go ahead and mark this off. H equals, and we'll fill that in. So before we do that, let's just go over here and do a side calculation. So let's go ahead and solve for x. So we have x squared over a squared equals 1 minus y squared over b squared, just like you did in pre-cal. You know, when you do those formulas where they gave you the a or the foci and you had to find the equation of the ellipse and things like that. You know, lots of times when it comes to doing these types of problems, you're just manipulating the convention. And so that's what we're doing now. So first what we can do is get a common denominator. So we'll get, in this case, b squared minus y squared over b squared. Just clean it up a little bit to make the calculation a little bit easier. And now we can multiply by the a squared and then just kind of bring the b squared out to the left. So x squared will be a squared, and we'll just bring the b squared out, and that'll leave us b squared minus y squared. So just very straightforward algebra. And now, of course, this is the square root property, but we need the upper arc. So we're going to take the positive square root. So we'll just say select positive radical. And so now this will give us x equals, in this particular case, a squared over b squared ¼ and then the radical b squared minus y squared. So for now, we're going to select the positive. So when we go over here, we're thinking, okay, for a given y, we get this. And of course, now let's go ahead and do this. These are both positive numbers. So we get a over b squared minus y squared to the ⅛. So if you like, I'll go ahead and label this. So this is a over b squared minus y squared to the ⅛, comma y. And then of course over here we get the negative, just to remind you what we're doing. So here we have the y, but we have the negative. So we've got a over b squared minus y squared ⅛, comma y. So again, we have to make sure we cover the entire strip. So now we can fill this in. We just have two copies. So H will just be twice this, 2AB, B squared minus Y squared to the 1/2. So I'll just put a box around that. So again, just putting a little extra detail in there just to give everybody that sense of comfort. I mean, you sometimes when you're working with a curve that's simple like circles, you don't think about it. Ellipse is just like a circle, but there's a little less confidence because again, it's a little bit different. So now when we look at this, we're thinking, okay, shell method. So we've got all the particulars here. We have the interval of integration, we have the distance to the axis of revolution, and we have the length of the strip. So now shell method. So we have volume equals, again, we have our 2 pi. And now again, we go 0 to B, 0, B, distance to the axis of revolution, Y, and then the length of the strip, the height of the strip, 2AB, B squared minus Y squared to the 1/2 dy. Now, when you think about the calculation and you compare this to the last one we did, this is not nearly as complicated because again, we're not having to worry about an axis of revolution that is exterior cutting the region. So it's a much simpler problem. So now we can go ahead and clean this up and then multiply or do the adjusting for the integral. So now the 2AB can factor. So we have 2 pi times 2A divided by B, 0 to B. And now I'm going to go ahead and move the Y over, then we'll adjust it. So we'll have B squared minus Y squared to the 1/2, and then we have the Y dy. Now this is looking really good, but again, we want to set this up to make it table ready. So we can see here that if we think of U equals B squared minus Y squared, then du will be negative 2y dy. So we don't have the negative 2y, we have the y, so we can make that adjustment. So now we can say, well, we've got the 4 pi a, so 4 pi a over b. And then of course we need to input the negative 2 and then pay for it. So we'll have a negative 1/2 or 1 over negative 2, 0 to b, and now we have b squared minus y squared to the 1/2, and then again put in the negative 2 to make it table ready, dy. So we've done this a million times. This is actually not too bad. So this is table ready. So you can think of a lot of what we do in this chapter as physics type problems and engineering type problems where we just basically manipulate the geometry, the analytic geometry. So now this is table ready, so we can add 1 divided by the new power. So let's just see, I'll work here and then we'll work down here. So of course, now we have the 2, which gives us 2 pi a b with the negative. So we have negative 2 pi a over b. And now we add 1 divided by the new power. So the new power is 3/2. So division by 3/2 is 2/3. And so this gives us b squared minus y squared to the 3/2 evaluated 0 to b. So these are kind of fun. You know, if you did the derivation for the volume of the sphere, you see a similar calculation here. So now let's go ahead and complete this. So notice here, we have the negative, we'll get the 4 back, the negative 4a pi, or negative 4 pi a. And then, of course, dividing by 3b, just keeping track of all the numbers. And now, for our upper limit, of course, if we replace the y with the b, we get the b squared minus the b squared. So that's 0. So I'll just go ahead and say this will be 0 to the 3/2, and we're done with that. And then minus, now we'll substitute 0. So we just get b squared minus 0 squared to the 3/2. So now we have negative 4 pi a over 3b. Now, of course, here, when we look at this, we have another negative. So we have the negative b squared to the 3/2. So, of course, now the 2's will absorb, and that gives us a b cubed, negative times negative. So we've got positive. So we have 4 pi a over 3b times b cubed. Again, the 2's absorb, the negative times the negative gives us a positive. And now we can see that the b will absorb one of the b's here. So this gives us 4 pi a, now 2 copies of b divided by 3. Now, the thing again that I like about this, which is similar to the torus example, is that we get to use a lot of convenient analytic geometry. Let's face it, we like to make models that at least where we can do some adjustments, or we can say, okay, this is close to this geometric figure to simplify our arguments. And so if you're familiar with the Mormon tabernacle where the choir sings, if you look at that tabernacle, it is in the shape, the actual dome of the building is in a shape of an ellipsoid, so that the room utilizes the sonic effects, the reflective properties of the ellipsoid. It is truly amazing when you sit in that room and the acoustics are like the choir singing right into your ear. Not only is it amazing with the reflective properties of the ellipsoid, but it was an amazing feat of engineering to even build it. They have videos of how they actually constructed it and how they've gone in and retrofitted everything so it will be stable for many more years. So this is a calculation you could do with the tabernacle. So the idea again is utilizing the basic analytic geometry. And then of course now, once you have this formula and you've created the ellipsoid in this manner, revolution about the x-axis, you can just substitute your a and b. So once you do all of this calculation, you could go to the tabernacle and ask them, okay, what's a and what's b? Or maybe they'll say you'll have to measure it, and that might be kind of difficult. So the idea here again is utilization of the shell method to compute the volume of a solid of revolution. So I think this is a fun topic, and maybe something that reminds you of why you want to be a STEM professional, why you want to be an engineer, or maybe you want to be a computer engineer or computer scientist or math professor, or some of you may even want to be physics professors. So nice calculation. Now, I want to do an example of another type of calculation where we're not, maybe so concerned with a lot of analytic geometry, but a function that you're going to see more of. And this one I think is just interesting in the sense that you see it a lot with normal distributions and probability distributions. A lot of you, when you go to the university, will take more mathematics, maybe some real analysis. Some of you will take probability theory, especially if you get into computer engineering. And let's face it, that is the boom field right now. Computer engineering is just blown up. So that's why you're working hard now, so you can get your university degree and change the world. So now here's another example. It says revolve region about the y-axis. So let me write this down. Revolve. And then next class we'll talk about arc length. I may just have a little time to introduce it, and that'll be fun. Revolve region about the y-axis. And here's the region. This is where we get this probability distribution function. We have 1 over the square root of 2 pi. That's to normalize it. E to the negative x squared over 9. So that gives you, hopefully you'll get an x so you can do a nice substitution. And then we have the x-axis, we have the y-axis, and we have the vertical line x equals 1. And then it says compute the volume of the solid of revolution. Now, one thing that we depend on a lot in this class is getting a cheap sketch, so to speak, using our college algebra. So we know this is a decreasing function. It's nice and symmetric relative to the y-axis because of the square. So this is what we think of as the normal probability distribution function, or a form of it. And so this will be a nice example. And in this case, this will be a nice example of the shell method. So let's go ahead and draw a picture of this. We'll get half of the function. Again, we don't have to be Rembrandt. We just have to have a reasonable sketch. So we'll spread this out a little bit. So now if we look at this, when we see x is 0, because we've got x equals 0 here, we just get a 1. So we get 1 over square root of 2 pi. So I'll just spread this out, even though this number is certainly less than 1, I'll spread it out so we can see it. So this is 1 over the square root of 2 pi. Now, this is a nice decreasing function. So we'll go ahead and draw in, and it's going to have a nice shape and a nice, point of inflection. And of course, it would be duplicated on the other side by symmetry. And now I'll go ahead and draw x equals 1, just to spread it out so you can see it. So we have x equals 1, x equals 0, and then of course we have y equals 0. So now you can see that the region is right here. Okay, so one thing that's interesting about this particular problem that you see is that the shell method is really nice here. We know at 1 here, we'll get what? 1 over the square root of 2 pi e to the negative 1/9. So if you wanted to just write that point in just for grins, we don't need it, but this would just be 1 just so you can see the easy algebra here. But we're not going to need this point, but I think it's interesting just to go ahead and write it in if you think about it. Now, we want to revolve this region about the y-axis. And so now we're thinking, okay, well, this is set up. We don't, even though the function looks a little bit untoward, this is set up for the shell method. So now we can say, all right, well, x will just live between 0 and 1. And so we can mark an x and draw in the representative strip or rectangle. Right there. So the shell method certainly has its attributes, which we like. And so now we can see the distance to the axis of revolution will just be x. So here, P equals x. Remember, distance to the axis of revolution. And then, of course, we just need the height of the strip, and that again will just be given by the function. So h equals 1 over the square root of 2 pi e to the negative x squared over 9. Now, again, when it comes to these types of problems, when you work them, you like Dr. Gardner said, respect the notation, respect the mathematics, respect, keeping track of everything. That's really what we have to do in calculus. We got to keep track of all those numbers. There's so many numbers floating around, and that's what makes it a lot more challenging than maybe previous courses. So now we can say, we can actually write this down with the shell method. So let me just emphasize what we're doing. Always make sure you set down what you're going to do, or at least have it in your mind so that you work towards that end, okay? So now by definition, the volume, so this is going to be an interesting little figure, like a gumdrop again, something we've seen before, kind of make a house in this shape. So this will be 2 pi. Again, nice interval of integration, 0 to 1. And we have our distance to the axis of revolution. And then we have our h, the height of the strip. So we have 1 square root 2 pi e to the negative x squared over 9. So this is just a nice computation. Like I say, it looks difficult, but it's a very straightforward computation, but using some functions that we don't maybe utilize as much. We tend to focus on the algebraic ones and maybe a few trig ones, but right now we're kind of focused on the radicals and the algebraic structures. So now what we can do, just like we had before, go ahead and get rid of any factors here that we don't need to clutter up the integral, just like you did in your calculus course. So calculus 1. So we have 2 pi divided by the square root of 2 pi. And then that's going to leave us with what? We'll go ahead and rearrange this, and then we'll adjust it for table ready. So we have e to the negative x squared over 9 x dx. Now, when we look at this and we think about what we're doing, what's interesting about these problems is that we look at the algebra and it just reminds us of the simple ones we started out with. So there's no difference. Now we just have more pi's running around. Now, what I want to do here is make this table ready so we can think of u as negative x squared over 9. So du will be a negative 2/9 x dx, just using the derivative there. So now we need to place the negative 2/9 and then pay for it with a fraction in the integrand, also with the reciprocal of that. So now this will just absorb into here, giving us the square root of 2 pi upstairs. It's like saying 2 divided by the square root of 2. And then, of course, we'll reciprocate this and get a negative 9 over 2. And then 0 to 1. Go ahead and put in the factor of negative 2/9. So we get e to the negative x squared over 9, and then times negative 2/9 x dx. And so this is table ready. So with that, the e to the u du is just e to the u, our favorite integral. So now what we can see, and again, we'll get some absorption again, but I want to go ahead and rewrite this so it looks a little bit more user-friendly. So we'll have a negative 9, I'll just say square root 2, square root pi, and then the 2 here, we can just write as square root 2 times square root 2. Lots of times, if you just factor things, it's easier to reduce them without making mistakes. Just go ahead and use your laws of exponents. So we've got the negative 9, and we wrote the 2 as 2 factors of square root of 2, and then we wrote the radical here as the product of the square root of pi and square root of 2. And so this will just give us e to the u. So we have e to the negative x squared over 9. And we really do like our limits of integration, 0 to 1. So now notice here the square roots of 2 absorb. So we have negative 9 square root pi over 1 remaining square root of 2, which we can combine. So these absorb. And this will give us, now we can substitute 1. So this will be e. Again, the 1 squared is just 1, so that'll be a negative 1/9 minus, and then of course now we're going to substitute 0, so this will just be e to the 0, and of course that's 1. So now if you like, you can go ahead and multiply through by the negative. Let's go ahead and clean this up first. This will just be negative 9 times the square root of pi over 2, just combining these with the laws of exponents. And this will be e to the negative 1/9 minus 1 by definition. And then you can run the negative through if you want, not required. So we get 9 times the square root of pi over 2 times 1 minus e to the negative 1/9. Now, when you write your answer, a lot of times, like I say, go ahead and work to the exact response. And then if WebAssign says approximate, do it. Feel free. But go ahead and work to the exact answer. So what we're seeing here, not only does the shell method give us really nice ways to compute certain geometric parameters that we didn't really have at our disposal before, we actually get some really nice practice with integrating. And again, just using the basic constructs that you learned in Calculus 1. And then of course, if you throw in some of the new stuff we learned with the inverse trig functions. So take the opportunity with these problems to practice your integrating techniques, practice your basic college algebra. I think the example, let me see if I can find it. I thought this was really a neat example here where we got to use our college algebra. Again, I used to tell my students, I said, you learned everything you needed to know in college algebra. When we think about these curves here, this basically is utilizing the decreasing nature of the exponential that we learned in college algebra. And of course, you can beat this up with a lot of calculus, but that's not required for this problem. I mean, we have to do calculus to solve it, but certain calculus aspects are kind of low level. We use that college algebra to set up the problem, to get the P and to get the H. And then we move forward with the shell method. So now what you're going to find is that as you work through these examples, the disk method is going to make a whole lot more sense, the washer method, and then work some of these, and then they kind of build. So for the next class, what we're going to do is we're going to talk about how we can compute the length of a curve. I mean, you know how to compute the length of a line segment, but we're going to extend that to general curves, and then talk about finding the surface area of a surface of revolution. So now remember, every time we create a solid of revolution, we create a surface. And so we're going to use the concept of arc length along with the revolution construct to figure out the actual surface area, or the area of a surface. And so I think what you're going to find is that all of these arguments we're going to be able to generalize later in calculus 3 to make them even easier to use. And when you do your differential geometry at the university, you'll see, oh man, I'm so grateful for calculus 2. That's when I learned everything the first time. Okay, so what I'll do, ladies and gentlemen, thank you for your attendance today. I will send out email invitations. I've got 2 conference hours today, one early and one in the evening, to accommodate, crazy schedules like work. I mean, we all have our part-time jobs and things, and taking care of younger brothers and sisters and relatives and all that. So I will send those out. And I will also post some information about our first test. So that's going to occur next week. So you'll have some information about that. But don't be a stranger to the conference hours. That, remember, they're set up for you, and they're for you to ask questions and to breed a little bit more comfort in what you're doing. So everybody have a great day. Enjoy the nice, cool weather. Just remember, it won't last very long. So I'll see you at the conference hours. So take care.